Oh, great, I'm glad you're here. Today, we're going to be talking about projectile motion. Come on, I'll meet you inside. What were we going to talk about again? Oh, that's right, projectile motion. Now, projectile motion can best be described as an object moving through the air in a parabolic arc. Just think of a baseball being hit by a baseball bat. The ball is hit with an initial velocity, and it travels through the air, reaching its highest point until it hits the ground. At each moment that the ball is in the air, following some path, it moves up some vertical distance, and it moves over some horizontal distance. Think of this as dissecting the ball's motion along the arc. It has some vertical component of the velocity pushing it upward, and some horizontal component pushing it forward. So, when the ball is hit, it has some initial velocity that can be separated into a vertical and horizontal component. And as the ball moves through the air along the arc, gravity is actually pulling against the vertical velocity. It begins to move upward less and less until it reaches its highest point. And after that, the ball begins to move back down to the ground. But remember, while this battle is going on, the ball is still moving forward. It is important to understand that gravity does not affect the horizontal component of velocity. So what's left to affect it? Air resistance.
You can think of air as really, really thin water. When I move through the water, my movements are slowed by the resistance of the water.
Air works the same way. Lucky for us. We are working with ideal projectile motion, which means that we can assume air resistance, among other things, to be negligible. Ah, negligible. A physics student's favorite word.
Our love, it isn't at all negligible. Can't you see, you and I are not negligible. Except for you, you are negligible.
You didn't see that. So these are the equations we use when we're dealing with ideal projectile motion. Now let's go over those equations real quickly. The height of the object at any given time is given by the initial velocity, multiply the sine of the angle, multiplied by the time, minus 1/2 the gravity multiplied by t squared. The range of that projectile is given by the initial velocity squared, multiplied by the sine of 2 times the angle, all over gravity. And the maximum height is given by the initial velocity squared, multiplied by the sine of the angle squared, all over 2 times the gravity. Now that we have an understanding of what exactly happens during ideal projectile motion, let's go out and actually put this into practice.
Hey, I'm over here.
Wow.
Apples. They're not just nutritious, they're also for firing out of cannons, and that's what we're going to be doing right now. We have an apple cannon right here, and it's my stepfather, Dave Baldwin. And Dave, why don't you tell us how the cannon works?
Okay, it's got a little igniter here. When you spin this, it sparks. We're going to spray some starting fluid inside, and then we'll put the cap on, and then we'll spin the igniter, and it should shoot the apple core out. We'll see.
Nice.
That was a short shot.
We're not only just going to shoot the apple out of there, I'm going to try to predict, using our equations, exactly where that apple's going to land. We're going to need one very important thing, the initial velocity of the apple coming out of the cannon. We're going to need two things for that. We're going to need the time that it takes for the apple to get from the cannon to its highest point, and we're also going to need the distance it travels during that time. So what we're going to be doing is we're going to be aiming the cannon at a 90-degree angle to the ground, directly upward. I'm going to go out 100 feet, and I'm going to use this little homemade inclinator to create a 90-degree triangle between myself, the cannon, and the height of the apple. And using the angle between me and the apple up there, I'm going to use trigonometry to find the height of its path.
Alright, let's do it. 64 degrees. I need the complementary angle.
Great, alright, let's go do some calculations, huh? Okay, so we got an initial velocity of 32.5 feet per second, and the range I calculated for that was about 32.8 feet. We're going to do a second one, just to maybe average the two initial velocities.
Oh, whoa! Heads up!
We can't use that one.
I cannot.
Here's our poor cannon fodder victim. That's all that's left of him. Alright, we're gonna do a third trial and see if we can actually get an angle on that one. I think that apple's still in orbit up there. Houston, we have an unidentified apple floating out here.
Test number 3, let's do it, quick!
Go. Oh, that's good.
107 feet. What was our time?
6 seconds.
So the first range I got was 32.8 feet. The second range is 72.5 feet. Let me calculate the range, taking the average of the two initial velocities. We have this rope marked in 25-foot increments. Should be 50 feet. It looks like, I think it's going to go way further than that. Let's just take an uneducated guess. This is just going to be my random prediction using just judgment of distance. It went way farther than I even thought it would. Math, why have you failed us?
Dragging the rope out to get an actual distance that the apple went.
So 150 plus another 60. That went over 200 feet. That is pretty frickin' far. The only thing I can really think of is that the initial velocity of it coming out of a cannon facing straight up as opposed to one at a 45-degree angle, it's going to be a little different because this apple is going to have to overcome a bit more gravity than this apple is. So we're probably getting a faster initial velocity coming out of the 45-degree cannon. So with a higher velocity, it's going to go further. But as much as that, that's it for Mr. Physics. Thanks for joining us. We'll see you next time.